Okay. All right, guys, ready?
No one cares about Tom Brady, yes.
Okay.
I agree with that statement.
What's your only pencil?
Yeah, other than this, you can have it. That's from Vance, probably.
Listening. Zogis is still not responding to me.
Oh, yeah. Well, the booster means then what, 7, so when it's over.
It's so annoying. How?
Yeah, I emailed them, like, yeah, I can't
I
get
saw your
it.
email. I didn't respond, but I saw your email.
I'm gonna call him. I have his phone number. I'm just gonna straight up call him.
Let's not be calling anyone. Sit down.
Often I was like,
I only get
Hey,
one circle.
turn the security cameras off. No
I
catching
actually-
throwing chairs.
So where we left off the other day was we were talking about energy. So we got through we got through all the frameworks, and then we got to energy. So basically, there's two frameworks we need to talk about here that are similar. It's work and energy.
So, should we make the category work and energy?
I would. In the textbooks, it's chapters 7 and 8. 7 is basically work, and 8 is, conservation of energy.
Yeah, but you got.
What chapter are we on technically in class right now?
10, 11, and 12 are really one kind of thing.
How many are there?
We're going to touch on 13 a little bit, and we're going to touch on 15 a little bit, but we don't do the full of either of those.
Good, because I saw the practice tests on this.
yeah, there's like,
So we'll do 13 next week, 15 the week after that, and then
Bob's your uncle.
And then Bob's your uncle, exactly.
And then I cry myself to sleep till I do anything else.
Well, then there's 2 weeks after that. So if it takes a little longer on one, it's not that big of a
what do we
deal.
do after they do that?
I'm going to teach you guys how to program in VPython.
And then we're gonna build boats.
Didn't you used to do that every Friday?
Yeah.
See, I know everything.
All right. So let's talk about work. Well, let's talk about energy. What is energy?
Or-
So, so we didn't do this in here this year, although I often do this with students, but I do it with teachers also. I said, just, you're a professional high school teacher, real quick, write down your just definition of
That is the
energy.
hardest question you could ask someone.
Listen, man, you're a professional high school teacher. You teach about energy every year. You've been doing it for 15 years. You have to have a definition of energy. Just write one down. And they look at me like I'm a crazy person. But many teachers will write this. Many teachers will write like,
Welcome to physics.
energy is the ability to do work. And I was like, okay, that's fine. If energy is the ability to do work, then quick write a definition for work. And then they write, well, work is the transfer of energy. And I'm like, I don't think you can do that. Right? I literally don't think that's something you
What's
can
the
do.
definition of energy?
Who said
Well,
this?
it's
High school
something is
teacher.
energized.
Yeah,
So where we end up with is this idea that energy is a very nebulous concept, and it's not a physical thing. It's not an ability to do something. My friends that I know that teach this stuff say, well, it's the invisible stuff that makes stuff do stuff. That's
Wow.
not helping,
Wow, thanks for that.
right? You see how that doesn't really help?
Seems legit.
Well, I see what they're
I'm gonna write that on my AP test. What if they have a question? What is energy? It's the invisible stuff that makes stuff do stuff.
Exactly.
Listen, man.
They give me a 5 right there, and they're like, "This kid's a genius."
This kid gets it.
Are the tests gonna be like this from now on, or?
Just for tomorrow's testing.
Oh, yeah, that's right.
Oh, I just find
Yeah.
But
How does it?
we say energy is a framework that helps us describe the motion and interaction of objects.
That's the definition.
Okay, it doesn't matter what the definition is. For us, we're going to use it as a framework to understand and describe the motions and interactions of
You
objects.
say nothing,
Is that cool? Work, I think, is the best definition of work is work as a definition. It's the amount of energy that gets transferred within and outside a system. So let's talk about the way that we represent these things mathematically, and I think that it'll help us understand. So we have some energy. I don't know, forms is such a stupid word, but we have this one. What's this one?
Forms is like whatever.
Potential.
This is
Gravitation.
gravitational potential, and how do you solve for this one?
MGH.
So we use MGH. It could also be MG delta H. Because of the fact that we're always looking for a change in height. So oftentimes you'll see it like the change in your gravitational energy is mg, so it's referenced by your change of height. But if you measure these things from 0, then the energy is the absolute energy. Does that make sense?
Yeah.
No.
Who's struggling?
Claire. Claire.
Just got called.
Sorry, one of Disgusting.
I have 3 now, I
Oh,
think I need 3.
well,
Oh, I
Hey,
have
sir.
one too.
if you have 3, I think 3 times is good on the count.
Hey, you
Oh,
got
yeah, give me this.
Yeah.
Why did I not think of
I need
this?
a
You know,
100.
3 times 0 doesn't get me.
Is this on there?
Oh.
Yes.
Yes.
Oh, K equals
Yeah.
1/2 inertia, rotational inertia.
Right.
times omega
Okay,
squared.
so another thing we have is we have this one. What's this?
Oh, there they both are.
Spring.
So this is the elastic potential energy. How do you calculate this?
Something.
1/2 kx squared.
It's 1/2 kx squared, right? What's the k?
The distance of the compression.
Good, it's either the compression or the stretch distance of your elastic object, usually a spring, right? And k is what?
Spring constant.
K is the spring constant. Now, one of the things that and we did it a slightly different way, but one of the ways that this always kind of comes up is, let's say you have a spring and you're gonna hang it on your pole here. Got it. Okay? So you hang it, and then you're gonna put a mass on it, okay?
145 pounds.
How much is this? Yeah.
Next question.
136.
Okay?
Oh.
So what we noticed is that this dropped a distance d, okay? This dropped a distance d, this has mass m. How do we solve for the spring constant?
We don't.
We do.
We do. Yeah, we did.
Wait, is that the before and after, or is that?
Yes, that's the before and after.
Yeah, wouldn't you set the gravitationally?
So this is not an energy problem,
Oh, wait.
this is a force problem.
Never mind.
So you get the forces.
So this is a block that's in equilibrium,
So
okay?
our F net's equal to 0.
Good, so if F net's equal to 0, so what is our F net here? What's pulling it up?
Force, normal.
Forces of spring.
Wait, no.
Oh, no, the force of the spring, what am I saying?
Okay.
What are you saying?
Force spring is up, and what's down? The gravitational force,
Yeah.
right?
Yeah.
Now, what does Hooke's law tell us? If you want to find the force exerted by a spring, how do you solve for it?
KX.
It's
That's
KX.
what I was thinking of.
That's right. This is Hooke's law. This is for a
Linear.
ideal spring. It's a linear
Yeah.
relationship.
Okay.
So I end up with Kx is equal to mg. So if I want to solve for the spring constant, it's mg over x. Is that cool? This is a standard problem that oftentimes shows up in an AP test. Where it's like, look, here's a mass, you hang it on a spring, it stretches this distance, how do you represent the spring constant?
So like, I know sometimes we have negative kx, does that come into play?
Oh.
So here's the difference. One of them is the force on the spring, the other is the force by the spring. Okay? So if I'm taking this spring here, which way is this little weight pulling it down? Or pulling it down? And which way is it stretching?
So it's,
Down.
oh,
Ah,
So the force by the weight on the spring, right,
Yeah.
is going to be opposite the force of the spring on the weight. Okay? Either way, it doesn't matter because we're solving for this value, so the negative doesn't really matter for us. The negative is just there to tell you that if you compress the spring, the compression is in, but the force by the spring is out. If I stretch the spring, the stretch is out, but the force by the spring is in.
So the force by the spring is always opposite to the pull, or
Always opposite to the movement of the spring.
Yeah.
That's why it's negative kx. Great question.
Oh.
Okay, so that's a standard spring idea. I like it. And then we have some other energy. What about what's the energy of motion? 1/2 mv squared, right? Now, if you have an object sliding across a rough surface, can thermal energy be generated?
Yes.
What do we call that?
The work of friction.
We call that the work done by friction, right? And how do we solve for that?
Force of friction times distance.
Good, very good. It's the force of friction times the slide distance. Cool? So good? Now, what about work? Right?
Mr. Pavetta, this is kind of off topic, but I was wondering if today in this hour and a half, we could go over like how you approach an AP Physics style problem when you do it. You know, like the step by step,
Yeah,
like just
approach.
kind of like, I see this, like give
Draw
us
a
little
picture.
key hints, because
Sure, we'll grab one.
I
We'll
feel like
grab
the
one and
hard-
we'll look at it.
I feel like the hardest part for me is
that is definitely the
starting.
hardest
Yeah.
part.
Starting.
I get this stuff for sure, I get the big stuff, but when it comes to an AP test, I'm like, where do I
I don't even know how to start.
But then when you start it, then I'm like, oh,
I
then
just
do
write
this,
down
this,
equations.
this, and go.
All right. How do you find the work? So work manifests in a couple different ways. Okay? Work manifests in a couple different ways. So if I'm gonna find the work, I know that in general, like, think about a puck sliding on ice. It's going at a nice constant speed. You're looking at it, its energy is constant. How do you change the energy of a puck sliding on ice?
You have to
apply
apply
force.
force.
You have to apply a force. If you apply it in the direction it's moving, you're gonna actually add energy to it. If you apply it the other way, you're gonna take energy away, right? So you need a force, okay? This force has to have some distance, okay? So these are two vectors, and we know that this is the dot product, okay? So the force in the distance, this is the distance the object moved while the force was being applied. Is that cool? How does this, so I'm gonna get then absolute value of F, absolute value of D, and then what?
Cosine.
Cosine of the angle, because cosine maximizes when the angle is 0 when they're in the same direction, right? And what's really cool about this is cosine also, or dot product also returns a scalar. So work and energy can be both positive and negative, but it doesn't have direction.
I finally understood like the dot product versus cross product when we did torque. I was like, okay.
So wait,
Now we have one
is it all
or the
based
other.
on like the direction of the vector?
Yes.
So cross product is if they're in opposite directions?
If they're maximized when they're perpendicular,
So
So
like
torque.
torquing it.
like
Yeah.
torque. Exactly.
But this is max.
Even when you were doing the wheel today, you were
In
going
the same?
straight down.
So it's
down.
180 degrees.
So
or
work
zero,
is always,
or That would be.
Maximized.
so linear is always
Not
dot product, and then like in angular torque is cross product?
So torque always has to be some version of perpendicular. Even if you're like this, it's only the perpendicular component that can apply a torque.
No, it's the same with cross product and dot product. Like-
Oh, cross product,
Like there's-
whatever the two vectors you are multiplying for cross product, okay? That is going to be a maximum when they're perpendicular to one another. Whatever two vectors you're applying, if the answer is dot product, it's gonna be a maximum when they're in the same direction. So parallel to one another. Okay. All right, so now, this is nice if the force is constant, right? Right? It's really nice if the forces are in the same direction, right? Or the force and distance are in the same direction. But if you have an object that is moving in this direction and the force is in this direction, F, D, there's your angle, right? If you rotate this force down, you're gonna get more. If you rotate this force up 90 degrees, you can't affect it at all, right?
You're
See how
talking
that
about
works?
the dot product.
That's the dot product.
Okay.
Okay, now, what if the force is not constant? What is our actual definition of the work? Well, the work is actually the area of an F versus X graph, right? The way that we got this thing is we said, oh, if this is the distance your object is moving and this is the force that's applied, if your force is nice and constant, where's the work done? Isn't the work the area? Well, what shape is this?
Square. Oh my God.
It's a rectangle, right? How do you find the area of a rectangle?
It's a sad life.
How do you find the area of a rectangle?
Length times.
It's base times height, right? So you just do F times D. That's where we got the F times D from. The problem is that they're both vectors. So you can't just do F times, you gotta do F dot D, because they're both vectors. Is that cool? So really, when we go to express the work is actually the antiderivative of the F dx function, right? So if you're getting